Okay, in this lecture we're going to learn about converting discrete master equations, special discrete master equations, that's the asterisk here, into Fokker-Planck equations. And we haven't really talked about Fokker-Planck equations yet. There's an enormous literature that we're skipping, starting from Langevin equations and building Fokker-Planck equations from that route. We're skipping that because in kinetics we can often go straight to Fokker-Planck equations by starting from a discrete master equation or from a deterministic model of a system with a distribution of molecular weights, particle sizes, etc. Okay, so these things are gonna sort of lead us into population balance modeling and all kinds of topics like that. They have an enormous number of applications, and this is a nice transition, I think, going from the kinds of kinetic models that you encounter in stochastic processes, the kinds of kinetic models that you encounter in these kinds of applications, for example, in polymerization and in nucleation and crystal growth, that allow us to really get an introduction to these Fokker-Planck equations. Now, the advantages of doing things this way, instead of, for example, keeping track of every molecular weight or following the kinetic Monte Carlo simulation of a master equation, is that the Fokker-Planck formulation affords simpler models, and it often gives you analytic solutions. Okay, we're going to start with this example. We have this simple discrete network of states, numbered 1 through n and on. We have transitions from state n to state n plus 1. Those are going to be happening at rate k plus. We have transitions from state n plus 1 back down to n at rate k minus. And of course, these transitions are also happening from states smaller than n up to n and back. All right, so this is the kind of discrete state model, discrete master equation model that we just worked with in our last video, for example, the Becker-Doring model of nucleation. So if we write down a discrete master equation for this system, it would look like this. So what we want to do now is to think of n as a continuous variable and see what happens to this equation. Now, in general, converting a master equation into a version with a continuous variable is going to be difficult, but it's quite easy to do in those special cases where the derivative of the probability to be in state n with respect to time only depends on the probability to be in nearby states. And that's exactly the situation that we have here. You see, the transitions are local. You're jumping from a state with index n to a state n plus 1 or n minus 1. And in those cases, then we can do this conversion by using a Taylor expansion. So the first step here is to write the probability to be in state n plus delta n, some nearby state, a small delta n, as the probability to be at state n plus first order, second order. And so this is really just expanding out that probability to be here as a Taylor expansion. And of course, if I want to do this exactly, this goes out forever. The second step is to collect all of these terms in the Taylor approximation, write them as an operator acting on p of n and t, and of course then there's a nice compact notation that's really helpful for going through and doing this and sorting all the terms in this way. So I've got this operator e to the delta n times the derivative with respect to n acting on the probability to be at n and t. Now, the advantage of doing this is that we can then go in and everywhere we see an n minus 1, a p sub n minus 1, we're going to replace it with an e to the minus derivative with respect to n. Everywhere we see an n plus 1, we're going to replace that with an e to the plus derivative with respect to n. Okay, now if we go back to our example, I've rewritten the master equation, just regrouped terms a little bit here. So we have the terms that were proportional to the k plus, the forward hopping rates, and the terms that were proportional to the k minus, the backward hopping rates. And that gives us this grouping, pn minus 1 minus pn, and pn plus 1 minus pn. Now, we can use this Taylor expansion to write this as k plus times e to the minus d dn minus 1 acting on pn. And the other term becomes the k minus times e to the plus d dn minus 1 acting on pn. Okay, so my equation now, you see, is starting to become quite a bit simpler. Because what's going to happen is that the leading term here in this exponential is 1. It's going to cancel with that one. The leading term in this exponential is 1, and it's going to cancel with that one. And what we're going to be left with is a term on the right-hand side that begins with first order derivatives in p sub n. We can take that up to whatever order we want, but usually it's convenient to stop at second order. Okay, now we're going to used that Taylor approximation, truncated it second order, and that's going to give us this approximation that 1 minus e to the plus d dn is minus d dn minus 1/2 d squared dn squared. And of course the signs flip then. If you have 1 minus e to the minus d dn, you get a positive first order term and still the negative second order term. Okay, so you use this in the equation above, and you can simplify this thing. Okay, now what we're going to do is we're going to rename these coefficients. We're going to call this one k plus minus k minus a drift velocity. Notice the sign reversal from what originally appeared in the equation here. We're going to call this one 1/2 k minus plus k plus. We're going to call that a... Man, you messed this up badly. Okay, so now what we're going to do is use this Taylor approximation in the original equation and simplify things to this. So you get a coefficient here that has to do with the difference of the two velocities, and that has to do with the sort of drift rate along the n-axis with a first-order derivative term. The second-order coefficients, they become something that tells you about how fast variance develops in the packet of the little population that's evolving in time will spread out along the n-axis, and so that looks kind of like a diffusion term. So this in many ways looks like a convection-diffusion equation. And what we're going to do is rename these coefficients, and sort of inspired by that interpretation. So we call this one a drift velocity, and this is k plus minus k minus. Okay, so notice that the sign is opposite of the way it appears in this equation. And then this one, we call this the diffusivity, the 1/2 of the sum of the two, the forward and backward rate constants. So then with these definitions, the diffusion convection equation that we get out of this, this is our Fokker-Planck equation in this case, is that the derivative of the population at n with respect to time is negative of the drift velocity multiplied by the derivative of the population with respect to n plus a diffusivity times the second derivative of this population with respect to n. And you guys have all seen this equation before. It gives rise to very simple solutions that look like a spreading wave packet, if you want, a little Gaussian distribution, for example. If you start from a delta function, it will spread out into a Gaussian and gradually move along the axis with the n-axis with velocity d, and spread out in time with a variance square root of 4 dt.